As a review before hearing some of the interviews, let's recall how the definite integral was defined from the problem of finding an area A of the region S that lies under the continuous and positive curve y equals f of x from A to B. An example is the parabola y equals f of x equals x squared from 0 to 1. To estimate the area of the region S that lies under the curve y equals x squared and above the x-axis from 0 to 1, let's use n rectangles. For simplicity, let's start with n equals 3. First, we divide the interval from 0 to 1 into 3 equal subintervals of width 1/3. Then build 3 rectangles. Each has the same width 1/3, but its height is the f value of the right endpoint of each subinterval. The sum of the areas of these 3 approximating rectangles returns an overestimation of the true area A of the region S. The notation R sub n indicates that we use the right endpoint of each subinterval to build the heights of these n approximating rectangles. Next, instead of using the right endpoint of each subinterval, let's use the left endpoint to build the height of each rectangle. The sum of the areas of these 3 approximating rectangles, L sub n, returns an underestimation of the true area A. Notice that we can repeat this procedure with a larger number of subintervals or rectangles to obtain better estimates. As n increases, the sum of the areas of these n rectangles becomes better and better approximations to the true area A of the region S. Therefore, the area A of the region S that lies under a graph of a continuous and positive function f of x on a given interval a to b is the limit of the sum of the areas of the approximating rectangles as the number of rectangles n approaches infinity. If this limit exists for all possible choices of sample points, such as right endpoints, left endpoints, or midpoints, we define the definite integral of f from a to b as this limit. One thing to note is that even when f of x has negative values on some subintervals between x equals a and x equals b, we can still form Riemann sums and take the limit. So the definite integral of f of x from a to b returns the net area of the graph between f of x and the x-axis from a to b. For more geometric representations of the integral, feel free to watch the video from 3 Blue, 1 Brown, linked below. To understand the importance of the integral and its diverse applications in Calculus 1, we asked a handful of Trinity students and professors about how they use integrals in their daily coursework or research. Here are their responses.
So if one knows, for example, a force law, the force being applied to some particle, then you know its acceleration, and through 2 steps of integration, you can extract the position. But additional places that this shows up is in the production of new principles. So for example, we sometimes define the idea of work as the integration of the force exerted on a particle along a path that it travels. So if I ask the force being applied over a given path and I add all that up with an integral, what I get is an energy. It determines the energy of the particle. And so you can use mathematical laws to extract new laws of nature from old laws of nature. And this is one way to do it.
Displacement is one of the first things that you use integration for, and then you kind of apply it to sort of similar topics as you increase your level of understanding in physics.
A really common task in modern computer graphics is to do realistic lighting, to figure out why an object looks the way that it does. And this is frequently done through something called the lighting equation. And the lighting equation is just trying to add up the contributions of all light sources and how it affects how a surface looks. Now, you can do this in a discrete way, right, with just a big sigma summation, but that assumes that all light sources originate from a finite point. And in reality, like a light bulb has a surface or a filament or some area that the light comes from. And so to make things look correct, you actually need to integrate over the whole surface of those lights.
Another example for this one is that over the summer, I did some research using in terahertz, and terahertz is a form of infrared light. And over the summer, they're basically lasers, but you can't see them. That's the fun part. So basically, I spent a lot of time aligning, basically that's an emitter and a receiver. And you spend hours and days and weeks aligning them to make sure you have the highest amount of intensity for the laser. And the best way to do that is to test how the intensity changes as you slowly move the receiver away. So the intensity goes from like, I don't know, like 60% all the way down to 0 as you move the receiver down. And that gives you like a nice little error function, like a change. It's kind of an error function is a very ill-defined function, but it basically is what it is. It's an error function. It shows how the intensity changes over time. And when you integrate that, you get a bell curve, you get a Gaussian distribution. And handy dandy concept of the Gaussian curve that you get from integrating the error function is it the full width half max, the width at half maximum of the curve tells you the diameter of your spot size. And that's also really helpful figuring out the intensity, because the smaller spot size means you have a better intensity. If it's bigger spot size, it's not as intense, which is not what we want for our purposes.
Integrals are really important for kinetics and also things like thermodynamics and quantum mechanics. So if we want to understand how much energy that's given off by a certain chemical reaction or burning a fuel, that's something that we need to do integration to understand. And even things like molecular orbitals or what is a chemical bond, all of that is based on relatively complicated integrals, but integrals are super important for all of those topics.
If you want to understand, let's say, a graph, you're limited in ways. Without integrals, you're kind of limited in how you can do it. Integrals allow you to understand, let's say, the area under a curve. Of course, that's the basic of what an integral does. But in my line of research and work, when you're dealing with electromagnetics, you need to use integrals to understand how much of, let's say, an electric field is flowing through an area or a volume of space. So this is an electric and a magnetic field moving in time and moving in space. You can see it's moving in time because it's changing right before your eyes. You can see it's moving in space because it's going somewhere. In this case, it's kind of moving along this direction. And the electric and magnetic fields are bound to each other through a relationship that you can use calculus to understand. And so that's the way that I, usually have to invoke integrals and differential stuff in my work.
We then asked the students and professors to talk about what they thought was the most important topic covered in Calculus 1. That is, what they believe is one of the biggest takeaways or consequences from the course. Here are their responses.
Probably the most important thing from calculus is the fundamental theorem of calculus, which is what actually equates the idea of an antiderivative with the area under a curve.
The most interesting aspect of Calculus 1 is the idea of continuity. That when applied to physics, when applied to the natural world, this idea that you can regard in certain respects the natural world is continuous, that I have some piece, some object, some material, and I can zoom in on it, and I can zoom in even further, and I can zoom in still further, and use the mathematics of continuity, which then gives you things like differentiation through limits and so on. It allows you to formulate laws of mechanics. So I think that's what I would say. Continuity is the most interesting topic.
Because as engineers, as some of our professors have put it, we like to linearize things because it makes it easier to model and extrapolate information, especially from data too, especially in research, you like to linearize things or whatever. So linearization, I will go with that because it makes things nice and straight. It's very easy to look at and interpolate and interpret data when they're linearized.
The most important is because the fundamental of calculus is, I cannot insist too much why it's important. It's because it asks a different set of questions. Okay, we have these weird shapes, say defined by a function. How do we assess the area, right? So that also is an important question to have. To answer. So in a sense, it helps you, but the fundamental of calculus goes on to be even much more important in different forms as you move on.
I really like how calculus was developed as part of physics, and physics and calculus were kind of developed together, and how, we really can't understand, the velocity or acceleration without calculus. And that's the fact that those two things are connected to each other just was the part that I think really made it feel like math was really connected to the physical world for me.
But what I found interesting was limit calculus, limit theory. The idea of a limit of some number of approaches kind of broke my mind a little bit. I had to wrap my head around the idea of numbers that are going somewhere but not getting there. And I also love calculus for exposing me to all the many ways that you can do 0 divided by 0 and end up with numbers that actually are finite. L'Hopital's rule is my favorite little trick from calculus, which let me understand how to do, seemingly undoable mathematical operations.
The applications of derivatives and I guess applications of integrals, because once you've learned that mathematical framework and once you've gotten good at just being able to carry out the process, then you start learning how to actually understand its uses. And so suddenly, instead of just being giving an equation, be like, oh yeah, I can take the derivative of that, you're actually given a situation where you have to think through it and think, oh, why am I taking the derivative of this?
If you understand the rules for derivatives given any function, you can find it. In fact, I think it's fun to write programs that do symbolic derivative type things because the rules are fairly straightforward. They can get complex, right? You can have very formulas that are challenging to apply them to, but the rules are somewhat straightforward.
I really think derivatives and integrals, just these basic relationships that allow you to understand the relationships and the definitions of displacement and velocity and acceleration. I think they're basic, but they're beautiful.